Let's start this podcast with a problem that doesn't seem like it should fit at this point in the class. Compute the double integral of the function x dA over s, if s is the sector below. And so it's part of a circular sector of radius 2, and it's the stretch between apparently 30 degrees and 60 degrees. Now, since this is a double integral, our best bet is to apply Fubini's theorem to it. Notice that it's not vertically simple, because when I draw vertical lines, some of the vertical lines have a straight top edge, and other vertical lines have a horizontal top edge. It has a circular top edge. By the same argument, it's not horizontally simple. So the only way that we could attack this kind of problem is by splitting it. So let me, for the moment, just split this in half, and we're going to attack this as a double integral problem. We'll integrate over the section S1, which we'll call the left-hand side, and then we'll do the double integral over S2, the right-hand side, and then we'll add the two results together. So to work these things out, let me draw this sector in greater detail right down here. So what we have here is we've got a circle of radius 2 on the outer edge. The equation for that is x squared plus y squared is equal to 2 squared. Since this is a 30-degree angle, and this side has length 2, basic trig tells me that this height is 1, and this length is root 3. So this has to be the point root 3, comma 1. It also means that this bottom line, which goes root 3 units over and 1 unit up, has to be the equation y equals 1 over root 3x, since we know its slope. A similar argument, since this is a 60-degree angle, this upper point right here has to be the point 1 comma root 3, and so this is the line y equals the square root of 3x. And so we'll subdivide our region right down the middle. Hence, if this is the region S1, we could go and describe S1 as follows. S1 is going to be described as a vertically simple region where the y values stay above the lower curve, which is 1 over root 3x, but below the upper curve, which is the square root of 3x. The x values, on the other hand, well, the leftmost x value will be 0, the rightmost x value will apparently be 1. And so since we've got this description of S1, then we know that the double integral over S1 can be expressed as an iterated integral. We'll take x, integrate it first with respect to y, from x over root 3 to root 3 times x, and then integrate that again with respect to x between 0 and 1. So let's go and do it. Starting with the iterated inside part, if we integrate x dy, we're going to get xy, which will evaluate from y equals x over root 3 to y equals root 3x. So that'll get us, plugging in the top value, root 3 times x, plugging in the bottom value, 1 over root 3 times x. If we put these guys on a common denominator, this is root 3x squared minus root 3 over 3x squared for a grand total of 2 root 3 over 3x squared. And so that's our inside iteration. So now we can go and integrate from 0 to 1 the function 2 root 3 over 3x squared with respect to x. So that's just going to get us 2 root 3 over 9 x cubed evaluated from 0 to 1, and if we plug in 1, that's 2 root 3 over 9. And so we found this first area right here as being 2 root 3 over 9. So now let's focus on the second stretch, S2. For the second sector, the y value has the same lower curve, the line 1 over root 3x, but its upper curve is now the circle. So if we solve the circle for y, since I'm trying to describe this as vertically simple, this becomes the equation y squared is equal to 4 minus x squared, or y is equal to plus or minus the square root of 4 minus x squared. But since I'm looking at positive y values, I'm in quadrant 1 after all, I don't need to consider the minus bit. And so the upper curve is going to be the square root of 4 minus x squared. The x values, on the other hand, well, the leftmost x value is 1, where we left off, and the rightmost x value, well, the rightmost point is this point, who has an x value of root 3. And so we've got the second sector, or segment of a sector described. We can now use Fubini's theorem to work out the integral over S2. It'll again be an iterated integral. We'll take x and integrate it with respect to y from 1 over root 3x to the square root of 4 minus x squared. And then we'll integrate that again from 1 to root 3. So let's focus on the inside bit first. If we integrate x dy, we're going to get xy, which we can then evaluate from y equals 1 over root 3x to y equals the square root of 4 minus x squared. If we plug in the top, we're going to get x times 4 minus x squared to the 1/2 power. If we plug in the bottom, we're going to get 1 over root 3x squared. And so that becomes our new iterated integral. We need to integrate from 1 to root 3 the function x times 4 minus x squared to the 1/2 power minus root 3 over 3 x squared dx. Now, because I'm subtracting two of these guys, I could really break this up as two separate integrals. And so let me do that. The second integral is a little bit easier to attack right here. If we go and integrate root 3 over 3x squared dx, we're just going to get root 3 over 9 x cubed, which we evaluate from 1 to root 3. So if we plug in root 3, we're going to get root 3 to the 4th over 9 minus root 3 over 9. Now, root 3 to the 4th power, that is 9. And so this just becomes 1 minus root 3 over 9. On the other hand, this purple integral, well, if we were to integrate x times 4 minus x squared to the 1/2 power dx, this would be a great candidate for u substitution. If we let u equal 4 minus x squared, then we would get that du is equal to negative 2x dx, or du over negative 2 is x dx. And so under the substitution, this would become the integral. Well, we'd have negative 1/2 du times u to the 1/2 power. That will integrate to negative 1/2 times u to the 3/2 power times 2/3, or negative 1/3 u to the 3/2 power. If we back substitute, that gets us negative 1/3 times 4 minus x squared to the 3/2 power, which we can then evaluate from 1 to root 3. If we plug in root 3, we're going to get minus 1/3 times 4 minus 3 to the 3/2 power, minus negative 1/3. If we plug in 1, we're going to get 4 minus 1 to the 3/2 power. So this first expression, well, this is just 1, and 1 raised to any power is 1. And so we're just going to get negative 1/3. On the other hand, this right here is nothing more than 3 to the 3/2 power. And 3 to the 3/2 power divided by 3 is just 3 to the 1/2 power, or root 3. And so that's this bit right here. And so we've just worked out that the second integral is equal to negative 1/3 plus root 3 minus the expression 1 minus root 3 over 9. If we clean that up a bit, we have 2 over root 3 times 9, or over 9, sorry, minus 1/3 plus root 3 minus 1 minus negative root 3 over 9. So negative 1 minus 1/3 would be negative 4/3. And 9 root 3 over 9 plus root 3 over 9 plus 2 root 3 over 9 would be 12 root 3 over 9, which simplifies to 4 root 3 over 3. And if we pull out of 4/3, this would be 4/3 times root 3 minus 1. And so there's our answer. Now, the point of this problem was not necessarily the integral itself. It was doable, although it did take breaking it up into subdivisions and a bunch of jiggery-pokery on the integral side. What I want to focus attention on, though, is the original domain itself. Notice that it wasn't vertically simple or horizontally simple, but if we connected straight lines from the origin, every straight line from the origin starts at the origin and ends at this outer segment right here. And so this object, while it's not very well described in terms of rectangular coordinates, would be really easy to describe in terms of polar coordinates. So remember that polar coordinates are the coordinate system r theta, related to the xy coordinates by the equations x is equal to r cosine of theta and y is equal to r sine theta. The basic idea is that every point in the plane is simply indicated by a distance from the origin r and an angle it makes with the positive x-axis. So if you were to take this sector S and describe it in polar coordinates by a system of inequalities, well, every point inside this sector has a radial distance from the origin that starts off at 0, but the farthest it could ever get is 2. So every point in this sector in polar coordinates has a radial distance between 0 and 2. Well, what about the angles? Well, every point in the sector, the smallest angle it could be, would be pi over 6. And the largest angle it could be would be pi over 3, 30 or 60 degrees. So this particular sector is actually very easy to describe in polar coordinates. So is it possible to convert an integral from rectangular coordinates to polar coordinates? That's the idea of this lecture. Let's suppose we've got a region in the plane, and we want to work out the double integral of some function f of x, y over this particular region. Now, up to this point, what we've been doing is we've been essentially taking the x-plane and chopping it up into even delta x subdivisions, the y-axis, chopping it up into even delta y subdivisions, and then using that to somehow break up my surface into small pieces whose volumes would be easy to compute. So the idea here is we were using the xy coordinate system and breaking up the x and the y components into small increments and using that as our building blocks. Well, what would happen if we instead used r theta and broke the universe up into small radial and angular increments? So, for example, to draw small radial increments, remember that r measures the distance from the origin. So let's mark off a couple of these guys, but notice that delta r's would therefore be measuring things in terms of sectors like this. Every one of these circles that I'm drawing are circles of a fixed radius, and so each one of these circles is changing by a fixed radius of delta r. What about delta theta? Well, remember, theta measures angles across here, so the idea here is take angles and subdivide them into small, evenly spaced bits of angle. And so each one of these guys right here would represent a common change of angle of delta theta. So how would this change how I go and do the integration process? Well, remember that the basic idea of the integration is you do a limit of sums of volumes of these sort of tall prism shapes, right? That was our basic idea right here. Well, what would the volume of a tall prism shape be if I subdivide the universe into shapes like this? So imagine we pick some sample point right here. Let's pick this particular sample point. And right now, I'm going to mark this sample point as being Ri theta I in polar coordinates. Remember the three-dimensional picture as well. You have this region in the plane, and you have some surface living above it right here. We've isolated a particular section in the domain, which we've represented in the three-dimensional picture as well. And what we're going to try to do is compute the volume of this tiny little shape right here. So the height of this shape is simply going to be the function value at that particular point. What about the area of the base? Well, if I look at this base right down here, this base is almost a square. How long is it? Well, this length right here is exactly what delta r measures. Two of its sides are exactly delta r. However, this length right here, the two other lengths, are not delta theta, because delta theta measures angles. And just sort of notice that this delta theta is the same here, as it is here, as it is here, as it is here. Delta theta stays the same, but the length of that segment gets longer the farther out you go. So how long is this segment right here? I'm going to make an approximation. The area of this, what's sometimes called a polar rectangle, is going to be approximately the base, which is delta r, times the height. Now, the height is part of the circumference of a circle. The length of that, according to geometry, is equal to the radius, which in this case is Ri, times the angle you work your way through. So it's not just delta theta, it's R times delta theta. The larger the radius, the longer this segment is. And that's completely consistent with my picture. If I'm really, really close to the origin, then that delta theta indicates a small section. If I'm really, really far from the origin, then delta theta is a long section. And so if I put all of this information together right here, what are the volumes of a tall prism? Well, the volume of a tall prism is going to be the height of the prism, f of Ri theta I, times the area of the shape in the base, which is going to be approximately Ri times delta R times delta theta. And so if I clean this up, we have the limit of the summations of Ri, f of Ri theta I, times delta R delta theta, where this is taken over all of the Ri theta i's in the region R, and then the limit is taken as the number of subdivisions gets larger and larger and larger. So it is possible to integrate a function in terms of its polar coordinates. The key fact about this is that you don't just take the function and multiply by delta R delta theta, but you get an additional R right here. You get a sort of what's sometimes called the polar scaling factor. So how do we take this double integral idea and apply it practically? Well, we need a Fubini's theorem for polar coordinates. And the good news is we've got one. So to describe Fubini's theorem, we're going to have to talk about regions who are radially simple, or sometimes called R-simple. What is an R-simple region going to look like? Well, it's going to be a region where if we take all of the lines from the origin, and we look at all of the lines from the origin inside this shape, then every single one of those lines will have a common inside curve here, 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 and then they'll have a common outside curve. And so you might have a region who looks like this. This would be an example of a radially simple or R-simple domain. And suppose we could write this inner curve right here in the form R equals alpha of theta. And we could write this outer curve in the form R equals beta of theta. Let's also say that this lower edge of this shape makes an angle of theta equals gamma. And the other edge of this shape makes an angle of theta equals delta. So a region who is radially simple can be written like this. The radial values will stay farther away from the origin than the curve alpha of theta, but closer to the origin than the curve beta of theta, whereas the angle theta will stay between gamma and delta. Then Fubini's theorem can be applied. Now Fubini's theorem will say that the double integral of the function over this region in its polar coordinate description can be expressed as an iterated integral. We're going to integrate first with respect to R from alpha of theta to beta of theta, and then we're going to integrate with respect to theta from gamma to delta. And the function we're going to integrate is going to be f written in polar coordinates r theta, but we're going to multiply by the scaling factor r. Now, it's worth pointing out that f of r theta is really sort of abuse of notation right here. F is a function of the variables x and y. And so what I really mean when I'm writing this thing down is I'm really saying take x and replace x by r cosine of theta, and take y and replace it with r sine of theta, so that we have the function f written in the form of r's and thetas. So a more precise statement would be to not write f of r theta, but to write f of r cosine theta, r sine theta. And this expression, Fubini's theorem applied to polar coordinates, is sometimes called the polar change of coordinates formula for integration. So let's see how we could use this on that previous example. So if we wanted to go and compute the integral of x dA for the sector below, we've already described the sector in terms of its polar coordinates. The radial values go between 0 and 2, the angles go between 30 degrees and 60 degrees. And so Fubini's theorem, or the polar change of coordinates theorem, would say that this is going to be an iterated integral, where we're going to integrate with respect to r first, where r goes from 0 to 2, and then we'll integrate with respect to theta from pi over 6 to pi over 3. And the function we're going to integrate is going to be r times this function expressed in polar coordinates. So x in polar coordinates is r sine theta. And so this becomes the iterated integral we're going to work with. So if we start on the inside, if we integrate r squared sine of theta dr, that's just going to get us 1/3 r cubed sine of theta, which we can then evaluate from r equals 0 to r equals 2. If we plug in 2, we're going to get 8/3 sine of theta. If we plug in 0, we're just going to get 0. And so this becomes the expression we need to work with. So now we're going to go and integrate from pi over 6 to pi over 3 the expression 8/3 times the sine of theta, integrated with respect to theta. So let's carry that work down here. If we integrate 8/3 sine of theta with respect to theta, that will get us negative 8/3 times the cosine of theta, which we then evaluate from pi over 6 to pi over 3. So if we plug in our values, we're going to get negative 8/3 times the cosine of pi over 3, or 60 degrees, minus negative 8/3 times the cosine of pi over 6, or 30 degrees. So that will get us minus 8/3. The cosine of 60 degrees is a half, plus 8/3 times the cosine of 30 degrees is root 3 over 2. So 8 goes into 2 4 times in both of these cases, and we're going to get negative 4/3 plus 4/3 root 3. And if we pull the 4/3 out, that's 4/3 times root 3 minus 1, which is exactly what we got last time. Compute the double integral of x squared plus y dA over the region R if R is the region shown below. So R is this particular shape right here, which is sometimes called an annulus, a section between two concentric circles. Now notice that an annulus is very easy to describe in polar coordinates. If we were to connect it with straight lines from the origin, then every straight line who comes out of the origin would have the same inside curve, the inner circle of radius 1, and they would all have the same outside curve, the circle of radius 2. And so this shape right here is actually fairly easy to describe in polar coordinates. The r values would stay between 1 on the inside and 2 on the outside, whereas the theta values, well, let's see, the most negative theta value we would get is a theta pointing down here at negative 90 degrees, and then we have all of the angles from negative 90 degrees all the way up to positive 90 degrees. And so the thetas will stay between positive pi over 2 on the upper end and negative pi over 2 on the lower end. And so now that we've got the region described in polar coordinates, we can use the polar change of coordinates expression. So let's convert this into an iterated integral. We're going to go and integrate this expression first with respect to r from 1 to 2, and then with respect to theta from minus pi over 2 to pi over 2. And we're going to integrate the expression r times the function x squared plus y, except that x squared plus y has to be rewritten in terms of polar coordinates. Now remember our polar coordinate conversions from a long time ago. X is equal to r cosine of theta, and y is equal to r sine of theta. And so I'm going to need to plug these two formulas into here, and we're going to get r squared cosine of theta quantity squared plus r sine of theta. And so if we clean this up, so let's focus on this inside iteration first. If we were going to go and integrate r cubed cosine of theta squared plus r squared sine of theta with respect to r, we're going to get 1/4 r to the 4th power times the cosine of theta quantity squared plus 1/3 r cubed times the sine of theta quantity to the 1st power, evaluated from r equals 1 to r equals 2. So if we plug in r equals 2, we're going to get 1/4 of 2 to the 4th power, which is 16, times the cosine of theta squared, plus 1/3 times 8r cubed times the sine of theta. If we plug in 1, we're going to get 1/4 times 1 times the cosine of theta squared. If we plug in 1 again, we're going to get 1/3 times 1 times the sine of theta. And so we're going to get 16/4 cosine squared minus 1/4 cosine squared, which is 15/4 times the cosine of theta squared. And we're going to have 8/3 sine theta minus 1/3 sine theta, or 7/3 times the sine of theta. And so that becomes the expression we'll plug on the inside. And so now we need to integrate from minus pi over 2 to pi over 2 the function 15/4 times the cosine of theta squared plus 7/3 times the sine of theta with respect to the variable theta. Fortunately for us, both of these guys are on the basic 20. If we integrate cosine squared, that's 1/2 of theta plus 1/2 the sine of theta times the cosine of theta. Whereas the integral of sine is equal to negative cosine of theta. And so we can simply evaluate this from minus pi over 2 to pi over 2. Notice that at 90 degrees or negative 90 degrees, cosine is 0. So this piece is a 0, this piece is a 0, this piece is a 0, and this piece is a 0. And so all we're really left with are these two terms. That is 15 pi 16ths minus negative 15 pi 16ths, for a grand total of 30 pi 16ths, or 15 pi 8ths. And so that's our answer. Well, if polar coordinates could be used for double integral, is it possible for our other coordinates to be used for triple integrals? For example, what if we had something that we could describe in cylindrical coordinates? Now remember that cylindrical coordinates are simply polar coordinates with a z component. So a point in three-dimensional space is described by an r distance from the origin, a theta angle, and then a z height up. And the polar coordinate formulas that relate the x, y's, and z's to the r thetas and z's are x is equal to r cosine of theta, y is equal to r sine of theta, and z is equal to z. Imagine we had some z-simple domain. So there's a top equation z equals t of xy, a bottom equation z equals b of xy, and we're looking at the set of all points between those two guys. But let's say that the domain r over which this thing is being plotted, the projection down in the xy axis, is something that makes far more sense to describe in polar coordinates. Say it's a sector of a circle. This would mean that it might be useful to describe the region D in terms of its cylindrical coordinates. So say we describe the region D as being z-simple. So the bottom surface stays between bottom of xy and top of xy, but that the region R itself is, say, radially simple. So we have that the radius stays between some inner curve alpha of theta, some outer curve beta of theta, and the theta stays between some values gamma and delta. Well, first off, notice that this is a bad description because I'm using not 3 variables, but I'm using 5 variables, x, y, z, and r theta z. I'm mixing and matching my 2 coordinates. But I could go and take my top surfaces, t and b, and I could rewrite them in terms of r's and thetas by using our polar coordinates. So imagine we have a surface expressed like this. Well, then Fubini's theorem would say that the triple integral of this domain of the function f of x, y, z would be equal to, well, we would first integrate the function f of x, y, z with respect to z from the bottom surface b of xy to the top surface t of xy, and then we would integrate the remaining part as a double integral over the region R. But if I focus on the outer part, the polar coordinates formula says that to do a double integral in polar coordinates, you would do an iterated integral, where you'd integrate with respect to r first and then theta, where r will go from alpha of theta to beta of theta, theta will go from gamma to delta, and we'll take r times whatever this expression is right here, written in terms of polar coordinates. So that means we'll take all of the x's, the y's, and rewrite them. So this expression becomes the integral from b of r theta to t of r theta, f of r cosine theta, r sine theta, z dz. Notice that since we're integrating this thing with respect to z, this r is a constant, and so it can be brought in front. And so the resulting expression, the integral from gamma to delta of the integral from alpha of theta to beta of theta, of the integral from b of r theta to t of r theta, r times f of r cosine theta, r sine theta, z, dz, dr, d theta. a combination of Fubini's theorem for triple integrals and the polar change of coordinates formula is called the cylindrical change of coordinates formula. And so it can be useful for integration over regions who are easier to describe in polar coordinates. Find the volume of the portion of the surface z equals 1 minus x squared minus y squared that lies above the xy plane. Now you might remember we've actually already done this problem once before as a double integration problem that involved a whole heck of a lot of stuff. There's an integration by parts and a trigonometric substitution. It was a horrible, horrible thing. But let's try to do this now using some of our new tools. For example, since we're trying to find the volume of some object, specifically this object right here, our work from the last lecture shows that the volume of an object is simply what the triple integral of the function 1 represents. So we need only integrate the function 1 over this shape. So let's see if we can describe this shape right here. Now notice that this shape has a clear top edge. The top edge is the surface z equals 1 minus x squared minus y squared, the parabola. And it has a well-defined bottom surface. It's the xy plane z equals 0. So I could describe the domain by saying that z stays above 0 but below 1 minus x squared minus y squared. Now I have to go and describe the region that it makes in the xy plane. That's the z equals 0 trace of this surface, and we've already seen that the z equals 0 trace of this surface is the equation x squared plus y squared equals 1, a circle of radius 1. But notice that this shape is quite naturally described in polar coordinates. It's very naturally described radially. All of the radial values stay between a radius of 0 and an outer radius of 1. And the angles we use, well, the smallest angle we would use is 0, and we have angles that go all the way up to 360 degrees. So we could describe the base in terms of r's and thetas, where the radial value stays between 0 and 1, and the angle stays between 0 and 2 pi. Unfortunately, this particular description isn't a good description for integration because we're mixing and matching the two coordinate systems. I'm using both r thetas and z's and x, y's, and z's, so I need to convert everything over into polar coordinates. But that's not too terribly difficult to do. The equation z equals 1 minus x squared minus y squared can be converted into cylindrical coordinates, by replacing x by r cosine theta and y by r sine of theta. So this gets us the equation z is equal to 1 minus r squared cosine of theta squared minus r squared times the sine of theta squared. Notice that if we pull out a negative r squared from these two pieces, we get cosine of theta squared plus the sine of theta squared, but this expression is equal to 1. And so this is just nothing more than z equals 1 minus r squared. And so I can replace this with 1 minus r squared, and we now have a cylindrical coordinate description of the region of integration. So according to the cylindrical change of coordinates formula, we can express this now as a triple integral, where we're going to integrate with respect to z, then r, then theta. The z value is going from 0 to 1 minus r squared, the r value is going from 0 to 1, and the theta value is going from 0 to 2 pi of r, the scaling factor, times this expression right here converted into cylindrical coordinates. Notice that 1 doesn't need any conversions. And so now we've got an integration problem. If we focus on this inside integral first, that should be fairly easy to work on. The integral of r dz is just rz, evaluated from 0 to 1 minus r squared. So that'll get us r times 1 minus r squared minus r times 0, or r minus r cubed. And so we can plug this expression into here and find that we have to integrate from 0 to 2 pi the integral from 0 to 1 of the expression r minus r cubed dr d theta. So if we focus on this inside expression, let's integrate r minus r cubed with respect to r. That'll get us 1/2 r squared minus 1/4 r to the 4th power, evaluated from r equals 0 to r equals 1. So we plug in 1, we're going to get 1/2 minus 1/4. If we plug in 0, we're just going to get 0. And 1/2 minus 1/4 is 1/4. And so that becomes the expression we need to plug in to here. So now we have to integrate from 0 to 2 pi the function 1/4 d theta. Well, that will just be 1/4 of theta evaluated from 0 to 2 pi. That would be 1/4 of 2 pi minus 1/4 of 0. And so 1/4 of 2 pi is pi over 2. And this is exactly what we got last time, but this integral was somehow, this integral was just much easier because we picked a better way of describing the surface. Find the mass of the ellipsoid 4x squared plus 4y squared plus z squared equals 16 lying above the xy plane if its density is given by rho of x, y, z equals z. Let's start off by drawing a picture right here. Now the problem says we're looking at an ellipsoid, and so that will help me at least sketch it. If I look at some traces, like say for example the z equals 0 trace of 4x squared plus 4y squared plus z squared equals 16, the z equals 0 trace would be 4x squared plus 4y squared equals 16, or x squared plus y squared equals 4, which means the z equals 0 trace is simply a circle of radius 2. If we looked at the x equals 0 trace instead, we'd get 4y squared plus z squared is equal to 16, which is an ellipse who crosses the z-axis at plus or minus 4, and who crosses the y-axis at plus or minus 2. And so that would be good enough for me to understand what the basic ellipsoid looks like. It's going to look something like this pill right here. Now the problem says we're only focused on the part of the ellipsoid who lies above the xy plane. And so this is the domain that the problem is talking about. So now that I have a picture for it, it asks us to find the mass of this shape. Well, from last time, remember that we said that the mass of an object is simply the triple integral of the density of that object. And so we need to do the triple integral over the set d of the function z dv. So all we need to do is describe the set d. Now notice that since all of the traces of this shape are circles, that would suggest that it's a good candidate for one of our circular coordinate systems. So let's see if we can describe D in its cylindrical coordinates. So to describe D in its cylindrical coordinates, let's first see if we can describe its top and its bottom. Its bottom is the plane z equals 0. Its top is given by this equation right here. Well, I need to first solve this for z. So if we take this and solve it for z, we'll get z squared is equal to 16 minus 4x squared minus 4y squared. Or if you'd like, 16 minus 4 times x squared plus y squared is equal to z squared. If we take square roots, we're going to get the square root of 16 minus 4 times x squared plus y squared. I'm ignoring the negative root because we're looking at the part above the x-axis. However, I can't use this formula because this is in terms of rectangular coordinates, not polar coordinates or cylindrical coordinates. However, remember that x squared plus y squared is r squared in cylindrical coordinates. And so this can be written like this. When I have it written like this, I also notice that I can pull out a 4 from both of these pieces. And so I can write this as 4 times 4 minus r squared, square rooted. And the square root of the 4 part will just be 2. So this can be simplified as z equals 2 times 4 minus r squared to the 1/2 power. And so we'll stick that right here. So now we've described the top and the bottom. So now let's simply focus on the straight down picture and describe the region over which we're describing all of this behavior. Well, we've already said that the base intersection was a circle of radius 2. And so in polar coordinates, that just means that the radii go between 0 and 2, and the angles go between 0 and 2 pi. And so this is a good cylindrical coordinates description of the region of integration. And so now we can simply set up the integral. The triple integral over the region W of z dv, according to the cylindrical change of coordinates formula, is going to be a triple integral. We're going to integrate the function r times this function z, where z is written in cylindrical coordinates. Well, z is already in cylindrical coordinates. so we don't have to do any rewrites. Now we're going to integrate this expression with respect to z, where z goes from 0 to 2 times 4 minus r squared to the 1/2 power. Then we'll integrate that with respect to r from 0 to 2, and then we'll integrate that with respect to theta from 0 to 2 pi. So let's work our way from the inside out. This innermost integral, we integrate rz with respect to z. We'll get 1/2 rz squared, evaluated from 0 to 2 times 4 minus r squared to the 1/2 power. So that'll get us 1/2 times r times 2 times 4 minus r squared to the 1/2 power quantity squared. Since this is a multiplication, I can put this square on both pieces. And so this will be 1/2 r times 2 squared times the square root of 4 minus r squared squared. And so that'll get us a grand total of 2r times 4 minus r squared, or if we plug this expression into here, the iterated integral from 0 to 2 pi of the integral from 0 to 2 of the expression 8r minus 2r cubed dr d theta. So next we can focus on this integral down here. If we integrate 8r minus 2r cubed dr, we're going to get 4r squared minus 1/2 r to the 4th power, evaluated from r equals 0 to r equals 2. So that'll be plugging in 2, 4 times 4 minus 1/2 times 2 to the 4th power, which is 16, minus, plugging in 0, we just get 0. And so that'll get us 16 minus 8, or 8. And so finally, our last iterated integral is going to be the integral from 0 to 2 pi of 8 d theta. That gets us 8 theta, evaluated from 0 to 2 pi, or 16 pi minus 0. And so that gives us a grand total of 16 pi units of mass. Well, what about spherical coordinates? The last of our coordinate systems. Imagine we had some point in three-dimensional space. Remember that spherical coordinates describe the location of this point in terms of a radius from the origin in three-dimensional space. The angle theta, its projection made with the positive x-axis, and the angle phi that the radial segment made with the positive z-axis. As formulas, these were x was equal to rho times the cosine of theta times the sine of phi, y was equal to rho times the sine of theta times the sine of phi, and z was equal to rho times the cosine of phi. So imagine that you had some kind of a domain who could be well described in polar coordinates. Say a domain who looked like this. The radial distance always stayed between some value alpha and beta. The theta value always stayed between a number gamma and a number delta, and that the phi value always stayed between, say, lambda and mu. So you had a domain who could be really simply described in terms of spherical coordinates. Well, we could repeat a similar style argument that we did for polar coordinates or cylindrical coordinates and come up with a formula for the triple integral over the domain W of a function f of x, y, z dv in terms of its spherical coordinates. And the formula for this is we're going to go and do an iterated integral. We'll have a spherical coordinate scaling factor, which is going to be rho squared times the sine of phi. And then we're going to multiply that by f of x, y, z. And then we'll integrate that with respect to rho, and then theta, and then phi. Rho going from alpha to beta, theta going from gamma to delta, and phi going from lambda to mu. Of course, written like this, we've mixed and matched spherical and rectangular coordinates, so we're going to have to go and take the rectangular coordinates in the formula for f and replace them with their spherical coordinate analogs. And so this will give us the final formula of the triple integral over the domain D of the function f of x, y, z dv will be the iterated integral of rho squared times the sine of phi times f of rho cosine theta sine phi, rho sine theta sine phi, rho cosine phi d rho evaluated from alpha to beta, d theta evaluated from gamma to delta, and d phi evaluated from lambda to mu. And so this particular formula right here is sometimes called the spherical change of coordinates formula. Find the volume of the solid Q that lies below the sphere x squared plus y squared plus z squared equals 9, and above the cone z equals the square root of x squared plus y squared. So let's make a picture to get some bearings here. This part right here claims to be a sphere. Notice that if we were to take any one of the traces, like the, say, z equals 0 trace, we'd get x squared plus y squared equals 9, which means it's a circle of radius 3 in the xy plane. And in fact, any one of the traces will get me that same sort of a circle. So what we see here is the orange expression is a circle of radius rho equals 3. On the other hand, this expression right here is supposed to be a cone, and I could kind of see that by looking at traces. If I looked at the z equals 0 trace, I just get the square root of x squared plus y squared equals 0, which is the point 0. However, if I look at, say, the x equals 0 trace, then we get z is equal to the square root of y squared. But the square root of something squared is the absolute value of that. And so in the x equals 0 plane, we would see the square root function. Put those two things together, the fact that it's a cone and that I can see what one of the traces looks like, and I see that the blue equation is this cone right here. So these two shapes will intersect sort of around this upper edge, and I can kind of get an idea of the solid I'm trying to look at now. Its top edge will be part of the sphere of radius 3. Its bottom edge will be the cone, and it will just hit the very, very base of the xy plane. And so this right here is the domain of integration. So to find the volume of this shape, all we need to do is do a triple integral of the function 1 dv over this particular domain. Now notice if we were to look at this domain, say, directly from the side view, in either the x or the y directions, we're going to see the exact same shape right here. We're going to see a portion of a circle. And if we look at it straight down the z-axis, we're also going to see a circular shape. Whenever we see something like this, when the views from the top and the sides are all portions of circles, that would suggest that an object like this might be well described in terms of its spherical coordinates. So could we describe, for example, where the radial values would always be? How far away from the origin can you be inside the surface? Well, the closest to the origin you can be is the actual origin itself at the very, very bottom. Every other point, though, can get at farthest to the outer shell right here. And the outer shell was a sphere of radius 3. So the radial values stay between 0 and 3. What about the theta values? Now remember, theta measures the angle from the positive x-axis. Now if we look straight down on our top view picture, the smallest angle theta we can get is 0. And then as we move around this cone, our angles can get larger and larger and larger until they get up to 360 degrees. And so the range for the theta values should be between 0 and 2 pi. Finally, what about those angles phi? Remember, phi measures angles from the positive z-axis. Well, since the z-axis runs right through the middle of it, the smallest phi angle you could have would be phi equals 0. And then the points get farther and farther and farther away. And so this angle right here would be the largest value phi you could get. But remember, in our side view picture, this was z equals the absolute value of x, if we took our y equals 0 trace. And so that makes this a 45-degree angle bend right here. And so that means that the phi values stay between 0, because I'm hugging the x-axis, or the z-axis, and 45 degrees, because that's as far as I can get. And so this domain right here is well described in spherical coordinates. So if we use our spherical coordinate formula, we're going to turn this into an iterated integral of rho squared times the sine of phi times the function 1, integrated with respect to rho, theta, and phi, where rho goes between 0 and 3, theta goes between 0 and 2 pi, and phi goes between 0 and pi over 4. So let's work out our iterated integral. If we focus on the inside iteration first, we're going to have to integrate rho squared sine of phi with respect to rho. Well, that just means we're going to have 1/3 rho cubed sine of phi, which we can evaluate from rho equals 0 to rho equals 3. When rho is equal to 3, we're going to get 27/3 times the sine of phi. When we plug in 0, we're going to get 0, and so that'll give us 9 times the sine of phi, which we can now plug in. That means we're going to have to do the iterated integral from 0 to pi over 4 of the integral from 0 to 2 pi of 9 sine of phi d theta d phi. But if we focus on this inside integral, to integrate 9 times the sine of phi with respect to theta, this whole thing is a constant. And so this is simply 9 sine of phi times theta, evaluated from theta equals 0 to theta equals 2 pi. So if we plug in theta equals 2 pi, we're going to get 9 times 2 pi, or 18 pi times the sine of phi. If we plug in 0, we're going to get 0. And so that becomes our next iterated integral. We're going to integrate from 0 to pi over 4 of 18 pi times the sine of phi d phi. Well, that's easy enough to do. That becomes negative 18 pi times the cosine of phi, evaluated from 0 to pi over 4. So if we plug in pi over 4, we're going to get minus 18 pi times the cosine of pi over 4, which is root 2 over 2, minus negative 18 pi times the cosine of 0, which is 1. And so if we clean that up, we can pull out an 18 pi, and we'll have 18 pi times 1 minus root 2 over 2 as the volume of this particular shape. Find the mass of the portion of the sphere x squared plus y squared plus z squared equals 1 in the first octant if its density is given by rho of xyz equals z. Let's start off by drawing a picture. So here's the xyz space. We've got a sphere right here, and if we do the same thing as the last example, this ends up being a sphere of radius 1. And then it says we want the mass of the portion of the sphere in the first octant. So that's just the part where x, y, z are positive, so the part bounded by the 3 coordinate planes. And so this will be the chunk we're looking at. This portion of the sphere right here. Now if we want to work out its mass is going to be the triple integral of this domain times the density function z dv. So let's work this bad boy out right here. All we need to do is describe the domain. Well, again, if we were to look at the domain straight down from the top, then what we would see in the xy axis is we would see this chunk right here, a portion of a circle. If we were to look at the xz plane, or the xz projection, then we would see this portion of a circle. And if we looked in the yz plane, we'd still see a portion of a circle. So the fact that every point of view we look at gets us sections of a circle would suggest that this is something that we could describe well in spherical coordinates. So let's see if we can do that. What would the rho values be? Well, any point in this thing either starts at the origin, or it can be farther and farther away from the origin, but it always has to end up on this outer shell, which is the circle of radius 1. So the distance from the origin can be between 0 and 1. What about the angle theta? So the angle theta, we need to use the top-down view here. The smallest angle we can get would be theta equals 0, because the x-axis is part of the shape right here. Then the angle can increase all the way up into 90 degrees. And so the theta values stay between 0 and pi over 2. What about the phi values? Well, the phi values measure the displacement off of the z-axis. So the smallest displacement is 0, since the z-axis is part of the solid. And then this angle increases until we get up to 90 degrees displacement. And so that tells me that the angle phi can also stay between 0 and 90 degrees. And so armed with this, under spherical coordinates, this triple integral can become the iterated integral of the scaling factor rho squared sine of phi times this function z, written in spherical coordinates, which is rho cosine of phi, integrated with respect to rho, then theta, then phi, where rho goes between 0 and 1, theta goes between 0 and 90 degrees, and phi goes between 0 and 90 degrees. And so now we have an iterated integral. If we focus on this inside bit first, then this becomes the integral of rho cubed times the sine of phi times the cosine of phi d rho, which means we have 1/4 rho to the 4th power times the sine of phi times the cosine of phi, which we can evaluate from between rho equals 0 and rho equals 1. And so at rho equals 1, this becomes 1/4 times the sine of phi times the cosine of phi, which we can then plug in here. Next, we need to integrate this portion. But notice that this portion is constant with respect to theta. So we're just going to get 1/4 sine of phi cosine of phi times theta, evaluated from theta equals 0 to theta equals pi over 2, which just means we're going to multiply this expression by pi over 2. And so now we're on our last iterated integral. If I pull the constants out, we have pi over 8 times the integral from 0 to pi over 2 of the sine of phi times the cosine of phi d phi. This is a quick substitution. If we let u be the sine of phi, then du will be cosine of phi d phi. And so this is just the integral of u du, which will come out to being 1/2 of u squared, evaluated from 0 to pi over 2. So the pi over 8 comes along for the ride. If we plug in 90 degrees into sine, we get 1. If we plug in 0 into sine, we get 0. And that gets us a grand total of pi over 16. And so there's our final tally.